Is this mic on, hopefully? So I thought today I would sort of just come and do a check-in on the sort of state of my own thinking, but maybe the state of machine learning research as it is. And of course, we don't need to talk about the slides. I can talk about almost anything. So if at any point you want to just have a discussion about something else, then let's do that. I'm happy to have a conversation about almost anything, and we can just jump topics as you like and need. But I thought I would give a short summary of searching for the reasonings of principles of reasoning and intelligence, and sort of one of the principles around which I design my own research and my own thinking. I thought I'd just say a little bit about myself. I'm Shakir. I'm South African, and I did my undergrad and a master's degree in engineering at the University of the Witwatersrand in Johannesburg. I did a PhD in Cambridge. I lived in Canada for a while to see what it was like to live in North America. And I've been at DeepMind since 2013, since we were a small startup, and have seen us grow and do sort of worked in many different areas of machine learning over this time. And these are the three pillars that I use my reasoning around. There's principles of reasoning, there are this area of global challenges, and there's one area of transformation. And I wanted to just thank you for the invitation to be here. I think these kind of spaces that we are in are very important. If you ask the question, how is it that we reach those principles and discover those principles of reasoning and intelligence, it is not because there are single lone genius scientists, but it is because we create communities like this that together we find those principles. So I think that's, I'm really glad to be here, and thank you for all being here. I wanted to quickly just tell you about another project that I do, which is run an organization called the Deep Learning Indaba. So now, the question for all of you to ask is, how do we create a global leadership in AI? So when I mean a global leadership, means that it is not located in particular countries, particular individuals, particular companies, but lives across the planet in many different countries, many different people, many different societies. So those kind of complex challenges, which only those societies will be interested to work in, are being done. And so this is sort of the work that we've been doing over the last 2.5 to 3 years about creating a new Pan-African organization to strengthen machine learning in Africa by building communities, creating leadership, and then recognizing excellence, which are the three pillars. And I think this kind of project that's happening right now is also part of that process of creating global leadership in AI. So one of the things that I think is really interesting about machine learning for me is that it gives us a pathway to go from principles to products. And I think this is what machine learning is. Given all the other definitions that you have, this pathway is very important. And those pathway begins at the very foundations, those principles, the probability theory that we spoke about earlier, issues of Bayesian analysis, hypothesis testing, estimation theory, asymptotic theory. There are various other kinds of differential geometry, etc., that can fit into these things. Then upon these principles, we then add this informational layer. How is it that we quantify uncertainty in our data? How do we know that we have gained knowledge and gained information when we've done an experiment? We heard a bit about the principles of causality. How do we test cause and effect and use that to make certain outcomes in decision making? And of course, the question of prediction, which is one of the driving questions of machine learning. And of course, then we come to those questions of reasoning. How is it that we do long-term planning by looking through sequences of actions? How is it, as we heard just previously, we create explanations of data that we have seen or experiences that we have? How do we do rapid learning from just very small amounts of data, which is the challenge which we are all facing? How do we simulate worlds, simulate environments, simulate possible futures, and use those possible futures to think about actions, and then objects, relations, how they evolve, what are those invariances? And of course, then we can get to the applications which we are interested in. Those applications which help us make money for the people who are bankers here, the other people who are startups, to deal with those fraud, those kind of global challenges around global governance. How do we advance our science through new ways of discovery, understanding new kinds of fundamental particles, the core questions of climate and energy, and all the other ones that we can think of. So these are those pathways, and for all of us in the room, we will start at different points in this hierarchy. Some may start in healthcare, some may start in fairness, and you will move your way down to pick and choose the thing that is relevant or not. Some of us may start at the bottom and move upwards, or start in the beginning. And I think it's just useful for us to reflect where in this hierarchy we are, what kind of tools we are using, the tools we are not using, and sort of how we build those kind of collaborations to help us explore that spectrum of reasoning. So when we think about the foundations of machine learning, then we will ask the question, how is it that we approach our machine learning research to build those applications on and advance those principles? And in general, I think as we just heard in the previous one, we will always aim to build a human-centered approach to AI. And I like this particular sort of hierarchy of thinking. It comes from cognitive science, and it's called Sun's phenomenological levels. And it sort of asks us to break our thinking into 4 different ways. It says that for any particular problem, any particular application, whether that is a brain or a machine or other kinds of biological systems, we can think of a physiological component. Where does that computation happen? Where does that action? So it's either neurons or in silicon. Then there are those componential aspects. What are the sort of key components? Is there memory? Is there prediction? Is there tasks? Then there are psychological elements. How is memory used? How do we do imagination and world simulation? How is it that we do planning and value estimation? And then there's the sociological level, and this is the reason why I like this one, because it recognizes that machine learning does not exist in isolation, that it lives in a society, that there are other actors, there are other agents, and we need to consider the impact of those other agents on ourselves and, of course, the impact we may have. And but in the machine learning core, there are typically today 2 ways of thinking about that. You're always, as far as I believe, a probabilistic approach and a pragmatic approach. And these 2 are the core. If you have been thinking a lot in deep learning, then one of the foundations of your thinking will be a paradigm called the architecture and loss framework. You will build an architecture which describes the data that you have, a processing pipeline. At the end, there is a loss, and the loss then propagates error. The one that I will talk about today is a different paradigm, which is called the model, inference, and algorithm paradigm. So instead, we should always think that there are models, there are inferential principles, and you can take any model and any inferential principle, or for the same model, many different inferential principles, and those combinations give us very different algorithms. And so these are the things we need to think about, because they help us to explore our spaces, do better comparisons, advance our science in the right way. So we heard about generative models, and generative models is one of the areas that I work in most. And there are many definitions of a generative model, but for example, if you're working in climate science, like I sometimes do, then a generative model will be simply a simulator of data. And if we're working in finance, we do the same, and similarly in physics, we want to build simulators of data in the world and then use those simulations to guide decision making. If I'm putting my hat as a statistician on, then I will talk about the problem of density estimation. That data in the world are things that we observe of probability distributions, and we can try and learn the probability distribution that is reflected in the world. And how do we do that? And then, of course, anything called unsupervised learning fits into this space of generative models. And they have several characteristics. A generative model, by its definition, because it must be generative, it must be random in some sense, must be probabilistic to handle that uncertainty. It typically is operating very high dimensions, images, video, text, entire streams of experience from multimodal sources. And then we are always typically interested in the distribution of the data. We're not interested in one particular outcome or one particular point in the set of parameters, but a whole distribution. And then the complexity of generative models comes in the fact that we need to have these distributions. So there are many types of generative models, and we just saw some of them as well. The easiest ones and the most popular ones, probably the oldest one, are called the fully observed models. You may sometimes call them Markov models or autoregressive models, depending on where you are reading. And they are very flexible, very powerful, can do a lot, but the alternative form is to have a latent variable model. And a latent variable model asks us to put some unobserved hidden cause, which we use to explain the data. So these are the 2 most popular types of models we have today. There is another class of models that we call undirected models. So if you are a physicist in the room, then these are the models which we use to describe physical phenomena, because we know that there are forces between electrons, but we may not know. There's no necessarily directionality And undirected models can be latent or fully observed. And then, as we also saw, there are the sum product networks as well, which ask you to create this alternating hierarchy of sum and product operations to do geometrical mixing. And of course, these two here, we could also call them deep generative models. And when I say deep, is not just that it is a hierarchy, which is one of the aspects of deep, but that they are built through these nonlinear functions and nonlinear compositions. And I'll do that. So when we think about these models, there are typically 4 operations that we will need to consider. And of course, the fundamental operation when we are working machine learning or data science or AI is called data enumeration. Where does the data come from? What was the sort of experimental regime that gave rise to that data? What was the sampling bias that is involved in that? And once we have the data, we can do 2 types of things with the data. We can usually ask what is called summarization. We can try and find all the ways that that data set we have, that stream of experience, is the same, what does it have in common? And that we'll call summarization. But of course, you could do the opposite. You could say, in what ways are each of these data points separate? Let's tear the data apart, see what is unique about every data point relative to another one. And then, of course, once we have a model and we have these kind of questions of summarization or comparison, the way we connect the data we have to the model that we have seen, that process is called inference. And this is the definition of inference. So typically, as I said, when we are thinking of data and summarization, we will just call that modeling. If we are thinking of data and this element of comparison, then we sort of enter a regime of experimental design, or thinking of the design of experiments. When we're thinking of summarization connected with inference, then we will talk about estimation and learning as a process. And when we do inferences for comparison, that's when we think about hypothesis testing or testing in general. And we don't do as much work in testing in machine learning, though I think we should do much more. So I think the point of this hierarchy is that there is a centrality of inference, because inference is the mechanism that combines the data that we have with the model that we have chosen. Inference then becomes very central, and then for me, the core question of building intelligence, of artificial general intelligence, will be those questions of inference. And AGI will be the most refined instantiation of these 4 statistical operations that we go through. And as I said, at the core question of AGI will be these questions of statistical inference, because they are the way that we do reasoning about data and experience. And there are many different kinds of inferential questions that we can ask. The most easiest one, or the most fundamental one, is just called the evidence estimation. Again, I said there's this question of learning the probability of data, and this is what the evidence is. We can do other kinds of things. Sometimes you don't want to know the evidence, you want to just know certain summary statistics, and we can do those by computing their means, their variances, and higher order moments. Parameter estimation is one of the key ones. There's the task of prediction, of planning if we were doing reinforcement learning, of hypothesis testing, which I just explained was a very central operation of experimental design. And what's interesting about all of these inferential questions is that we need to do a lot of work to figure out how to solve them. In each of them lives an integral that is usually very high dimensional, an integral that is very complex and unknown, and most of the work that we will do is to try and figure out ways of computing those integrals. And if any of you have good tricks for solving integrals, then there's a whole industry for you, and you can write many, many papers, and I think also advance the state of our knowledge, because those questions, inferential questions, are so central. And there are many different ways of doing integrals, as I said, if you could solve them. So statistical inference for me exists in 2 parts. You either have direct statistical inference or indirect statistical inferences. And these are the 2 ways of thinking of them. Direct statistical inferences are direct because there is the probability of the data, and this thing is the thing we target directly. We directly want to compute P of X, the probability of data that we have seen. And there are many, many ways. You may have heard of maximum likelihood, Laplace approximations, variational inference, if you are physicists, cavity methods, the EM algorithm, sequential Monte Carlo, and Markov chain Monte Carlo methods in general. They all attempt to directly compute the probability of a data set and then use it to do learning. Indirect inferences instead say, I don't want to target the probability of the data directly. I want to do this relative to something else. And relative comparisons are a very powerful way of doing things because they are often easier to do. And so we have equally an entire field of indirect inferential methods. Two-sample testing is the classical method that you would have learned in early statistics, the method of moments. Transportation methods are very popular these days, approximate Bayesian computation, and other kernelized methods in the RKHS, maximum mean discrepancy. So there's a lot for us to explore just in this space, but I think some of the new work that we need to do will explore what else is there beyond these methods, since they may not be working for us. And I'll come to the end to talk about what's not working and where the challenges of our thinking are. So if you were to try and use some of these things, we'll be able to explore a set of tricks. And I like to write them out as a set of tricks because it makes them very accessible, and it actually shows that the core computation is something very simple. And if you want to actually go through and derive all of these tricks together, I have a video of a far more longer talk where we go through each of these tricks in sequence and then derive them together to show the core computational tricks we can use to solve high-dimensional integrals and then use them to address complex challenges. So there are many familiar algorithms that you would have heard of. As I mentioned, the autoregressive algorithms, they simply directly target P of x. And in autoregressive models, we can easily compute this probability of the data. So learning becomes very easy. Because learning is easy, because we can write out this, we can compute the log of this quantity and then use the log of that quantity to drive the learning. These models can be very easy to use because they also don't require us to make other assumptions. And so if you have an Android phone, the way text-to-speech on your Android phone works is through this algorithm called WaveNet. And if you do it in production, you can actually make it run very fast. Although these models in general are very slow because they have to go through this sequential process. I think several weeks ago, a colleague of mine spoke about, in this meeting, variational autoencoders. And what's different with these models is now they are in this class of latent variable models. And they are one particular type of latent variable model. They are called prescribed latent variable models. And they are prescribed because at the end, we will always make this choice. We will choose a likelihood function, or we will choose a way of saying that when I observe data in the world, I will be able to know its probability, at least up to some constant. And knowing the probability or making a choice of that probability is very important, and actually a very important assumption. And so people will use a Gaussian distribution, a binary distribution, and several others. And the key element of variational autoencoders in terms of their inferential principle is that they are a direct method of inference, but because you cannot compute P of x, they will find a way of bounding this quantity P of x and instead do direct estimation on the bound of that quantity. And then we can derive all of the recent advances in variational inference over the last 5 years just through that key insight. And then you may have seen about the generative adversarial networks, which are a different way. They are a different kind of generative model. They are an implicit generative model. They do not make this final decision of a likelihood function. Instead, they are more directly a simulator of data. And the simulator, and rather than doing direct inference, generative adversarial networks use this approach of indirect inference. They compute P of x of your model in relation to what may be the true probability of the data. And this ratio that you can compute drives everything about learning in generative adversarial networks. And so these are three very popular algorithms that are currently the state of the art and represent the forefront of our thinking as it is in generative models. And there are many, many applications of these generative models, and I typically group them into three categories. There are generative models that we can use to build products. So they are super resolution, compression, text-to-speech, these kind of products. We have the uses of generative models to advance our knowledge of science, whether that's in proteomics, drug discovery, high-energy physics, astronomy, climate. And then there are those core reasoning questions of AI, which are planning, exploration, intrinsic motivation, model-based thinking, and RL. And I wanted to just look through a few of these for a short while as I end. So as I said, those assistive technologies are one of those core easy wins for us to do, because we do want to generate generate sounds based on text. And we want to have an easy pipeline that is simple, easy to train, scalable to hours and hours, hundreds of hours of data across multiple types of speakers, across multiple accents, across multiple types of voices. And these kind of models can work at that kind of scale and help us do generation. And I gave the example of the Google Assistant in this case. And those models are these fully observed generative models that I spoke about. There is, of course, I think, still to come to see its full scale, a new way of doing compression and communication as we think about the way data is being managed. And this is an example from some other colleagues who are looking at this problem of super resolution using generative models. And you can imagine in sort of more low resource economies, or when you need to conserve bandwidth, it would be good to send very low quality video, images, and then stream it across mobile devices, and then on the device do that kind of super resolution. And so I think there's a very interesting way of learning new ways of doing compression. Generative design, I think, is still also undefined and very clear, but you would have seen maybe the example from several startups, also here in our London economy, about doing generative models over molecular structures, or in general, other kinds of structured representational data. And now these innovative companies actually are able to compress this entire experimental life cycle into a very short period by having in one facility both the scientists who can generate these molecules and the lab themselves that can synthesize, and the chemists who can assay, and then you can fill this entire loop so you can experiment, generate new molecules, generate them, assay them, and come back. And I think there's just so much to do in this kind of space, and probably there's going to be something in Photoshop or all these Adobe things around this element of design and CAD design tools as well that we can do, AR as well. I think this is one of the reasons to be really interested in working in machine learning, because sometimes, as we spoke in the previous talk, people will take the work that you do and use them in very interesting ways. So this is a PhD student called Memo Akhtem. I think he's here in London at Goldsmiths, and doing a PhD at the intersection of machine learning and art. And as you can see, what's happened here is that there's a generative model trained on images and pictures, which is a conditional model of a scene to then generate an artistic scene. And I think it's just fascinating to see what people will do when we would ourselves have never imagined it when we are deriving those equations and computing those bounds. And of course, as we were talking in the previous talk, this is a very benign use of these technologies, right, of the work that we do. And what other sort of non-benign uses there are is an interesting question. I'm just going to forward this video because there's a part with fire which I think is really just fascinating to see. Yes, I think this part is just beautiful as well, which is phones, and it's like, I don't know, Sauron is quite evil, is unpleased. And then there's this section on daisies and lilies, and I think, just with the hand, I think it's quite mesmerizing. And then, of course, there is the question of advancing science, and many people are interested. One of the reasons we work on AI and machine learning is to understand both ourselves, our natural world, and so there are several different applications. If you have images from the Hubble telescope like this one, then the question there is, how do we discover new stars, new constellations that we have not seen before? And so you can do that through some kinds of anomaly detection using generative models. And here, these are called cosmology mass maps, and these is an image of the Large Hadron Collider. And in both of those cases, high energy particles are coming. There are hopefully new particles being emitted. How do you detect those new particles? And we need to be able to we can use generative models to simulate those processes as well. And there are other areas as well, fusion, and many other areas in sciences. And then I think one of the most interesting ones is probably in healthcare, the thing that really affects all of us, that affects the entire planet, that is one of those core developmental goals that we have as a planet. It's actually only one of the few goals that the entire planet has agreed on, that healthcare for all is important for us to do. And there are several ways that generative models are now having a role in thinking about healthcare. For example, in medical imaging, one of the things that we need to do, whether or not it is for explanation to the physicians themselves, to patients themselves, as well as to understand what the model themselves is doing, you use generative models to give alternative variations of segmentations. And in that way, explore the variability, use that as a mechanism of communication to patients and physicians, and build that kind of human-centered design. And of course, there's a lot of work going on in many areas. This is from a colleague called Suchi, who is looking at sepsis and the process of sepsis within hospital admission, and then using generative models to model the patient pathway through time, and then use those models to then inform clinical decisions. And again, the questions of causality become very important. The questions of explanation become important. The questions of safety and ethics become very important. And then generative models sort of have those questions then become relevant to our work in generative models. So what are some of the challenges that we are facing when we are doing this sort of health check of the state of affairs? As I said, one of the things that many people want to do is use these models as a way of testing new things, finding, is this something which is different from what I have seen before? And if you were to do a test of our models, so what you would do here is train a generative model on one data set, in this case, a data set called not MNIST, and you would evaluate that data set. It's just a data set of fonts galore. I don't even know how many fonts there are in there. And you can use the model, obviously, to give you a probability to score any data point that you have. Now, what you would expect from a functioning model is that if I were to give you a data point from some other data set which you have not been trained on, then when I score that data point, the model knows this data is not the thing I have been trained on. This data is something other, and its probability should be extremely low. But when we do exactly this kind of test, so I said we train on not MNIST and then we test it on MNIST, many of these models fail this basic test. They can do generation, but they fail to be able to distinguish in their probability that something is different from what it has been trained on. And so if we are going to rely on the log probability as a score, if we are going to rely on probabilistic judgments, then there's sort of something not right in the state of Denmark. And so this is one of the questions at the forefront of our research to think about. One of the other interesting ones is now to think about reinforcement learning and new ways of doing reinforcement learning. So there are many ways to think about reinforcement learning, but one of the ways of thinking of reinforcement learning is as a generative model. The generative model is very simple. It takes in actions, which we all would give, and the environment itself is that generative model, and out of the environment comes a set of observations, either a state itself, a visual scene of the world, or some rewards. And then if you think of this in the process of inference of the variational autoencoder that I spoke about, all the learning of a policy does is to do the inverse, to ask that inferential question, what is the probability of an action given the state that I saw and maybe the action? And so if you write out this problem, you use the tools of variational inference, you will get a free energy equation like this, and then you'll be able to immediately recover the famous policy gradient algorithm. So if we can recover the policy gradient algorithm, what other assumption, by changing our assumptions in this generative process, in the probabilistic model, what other kinds of reinforcement learning algorithms can we get? What other ways of doing exploration will we be able to do? What other ways of doing rapid learning at scale will we be able to do? And what other kinds of general environments we'll be able to learn in. So I think this one is sort of picking up over the last year, year and a half, maybe 2 years, and there's still a lot to do here because actually reinforcement learning is hard. If any of you have worked, it's pretty hard to get working. And then there are many other kinds of things. As I mentioned, inferential methods are very important. And so one of the things we've been exploring is an older approach, probably one of the oldest inferential methods called the method of moments, and looking to see how is it the method of moments can be applied when we consider our more modern problems and applications. Can we do mixed methods? Can we get the best of GANs and VAEs in one model? It turns out not quite yet. So there is a question to do there. Most of us are working on images and audio, and there are data sets which live beyond images and audio. Text, we heard earlier, was one of them. Networks of structured data is another one. There are other kinds of time series from finance, for example, that are interesting to look at, that have other kinds of correlations. So how do we build generative models that go beyond images, beyond audio, that have sort of other kind of noise, sparsity characteristics? Then there are many other questions. Representation learning is the one that everyone brings brings up when they want to work on generative models. We want to be able to learn some kind of abstract, generalizable representations of the world that we can then use in other tasks. And this question still is elusive despite a lot of work. We still cannot adequately evaluate our generative models or in general probabilistic models. And so there is a question there of how do we do an evaluation that is fit for purpose, that can help us solve and overcome some of those other issues that we heard. And like every other machine learning method, we still require very large amounts of data. And how can we move away from this area where we need large amounts of data to being more efficient, either through transfer learning or through just being inherently efficient? So thank you very much. I wanted to just give a very short overview of sort of those principles of reasoning where we looked at this model, inference, and algorithm paradigm, looked through that smorgasbord of inferential principles, and then did a short just update on where we are with our state of research in generative models, in their applications, and sort of some of the questions that we are currently looking at as we try and advance and use them to solve difficult and complex challenges. Thank you very much for your attention. Yes? I can repeat.
So thanks for a great talk about general machine learning stuff. It's really good. I was wondering if you could just share more about what are you working on currently?
I'm working on lots of different projects actually. I'll start with the sort of, if any of you are going to be at the Royal Society's Diversity Conference next week, you will hear me speaking there about other kinds of questions that we need to work on related to the transformation of our communities themselves and the work that we all have to do about diversity and transformation. So that's one bit that I do a lot of work in. But this entire area is my principal research area. So all those questions that I listed at the end are things that I am actually working on right now, thinking about how it is we do new kinds of evaluation for generative models. It's not quite working yet, but hopefully soon. Thinking about questions, this sort of fallacy that has come up where we cannot use our models to do anomaly detection, and how do we actually get good scoring that we can use to score models and use them to make decisions. That's sort of one thing I'm looking at. This intersection of probabilistic reinforcement learning is another area that I'm looking at. And then I'm doing some other projects as well in healthcare and in climate science. So I'm trying to touch it. It depends. You have to sort of jump because in every different problem you see a different kind of question. And after you've been working for a long time, you get bored, so you need to do different things. But I've been enjoying working much more towards the very application side to think about what it means to build clinically relevant questions. We can make all sorts of predictions, but what is a clinically relevant question? Or, just don't make a random simulation of the future weather. What is a prediction that is actually useful for building resilience to climate change and climate change? That question may sometimes subtly different, but figure out what that question is and how we embed that into our practice. I think what came up earlier was there's now a challenge where we don't know how to decide what is the good loss function. Because there are moral actors, there are sort of other decisions in place. There is now an interface between the policymaker who says what is allowed, what is doable, versus the technical person who defines a loss to say what is learnable. And there's an interface between sort of the policy and the doable, and I think there's a research question there as well. I don't have a deeper thought on that. There is some research in the old, so I think there's something interesting to look at there as well. And this is the reason to jump between fundamentals and application to explore that sort of intersection.
Hi. Just on the last slide, I wasn't really sure what you meant as on the bottom left about representation. You said the problem there, and you sort of went through quite quickly on that. And I don't know if you could just explain a bit more about what the issue you have with representation with current, I don't know if you mean generative models.
Mm-hmm. Okay, so the question is around what is actually the question of representation learning? And I think that's the question that I'm asking. When we say representation learning, even that question is undefined and unclear. So we will typically build a generative model with a latent structure, and we will call that latent structure through inference its representation. We'll then take that representation in another task, and then we will evaluate another task based on that representation.
Okay, sorry, if you can, could you give a concrete example of that, if possible? Just
So let's do the reinforcement learning example exactly. So the core question of reinforcement learning that has plagued people is the question of state representation. Right? So how is it that even though I have a visual scene, this is not the scene that I need to do action and to understand value, future value of things? So the question we need to do is then transform this scene into a state and then do reinforcement learning, value estimation, policy learning based on the state. So one of the things, so this is one of those elements of representation learning, which we will call the state. And then if we want to do that, we would try to learn a generative model, as we have done, over scenes from an agent in doing reinforcement learning, and then apply that to a subsequent stage. And so to what extent that's working, sometimes it works, sometimes it doesn't, and how do we do that a bit more robustly, and what are the principles of that? Right now we don't know the principles, which means it's very difficult to generalize to different kinds of environments, more complex settings, to settings outside of certain specific domains.
Okay, thanks.
Yeah, in the front.
Hi. So on one of your quite early slides, you said that probabilistic inference would be the kind of foundational core of AGI if we get there. And my question is possibly more of a hardware one, but do you think that we will actually be able to run those kind of simulations on traditional hardware with the kind of models we're building for this hardware, or are we going to have to wait for kind of the ability to simulate that fuzziness with more quantum-based architectures and more quantum-based algorithms?
There's a lot to unpack there. So nothing right now prevents us from using the current technology we have, right? And we can easily represent probabilities with the current approaches we have. So I don't think that's sort of the question. If you are thinking about what are the new kind of substrate for computation, I think one of the things that's interesting about machine learning is because we are exploiting the ability to do parallelization. If you are looking in the climate space, for example, they need very large, massive supercomputers because the way they are doing computation in what is called numerical weather prediction is through solving very large PDEs over time. And that is not a kind of computation that we can use, but we aren't quite doing that. And then if you go to the quantum space, quantum has different things. So the foundation of probability, as I've described here, is what is called the classical probability. So probabilities must be between 0 and 1. They must be normalized to 1. They cannot be non-negative. Quantum probability says you can have non-negative things because they're complex numbers. They don't, they must just integrate under the squared norm. So it's a very different thing. So you could use quantum probability to do classical algorithms like these, and then the nature of the computation won't change. But if you want to build a new kind of machine learning based on quantum probability as well as quantum algorithms, then you will need a new kind of thing, but then you'll also have to answer the question of what quantum data looks like. And quantum data, there's what's called a problem of reconstruction there, and we won't know how to reconstruct quantum data because all we have is classical data. So maybe something different is going to come in the future. I don't know. Yes.
Should we have one last question? Quick one?
Yes?
What do you think is the role of language in AGI? Is there any special role for language in a...
So the question is, what is the role of language in AGI? Of course, language is, I guess it depends on your worldview and sort of what you want to get out of an AGI. Or if we define this kind of general intelligence as the ability to do many different tasks simultaneously in one agent, then you could answer that question in many different ways. But I think language has given us one of those ways that also came up in the questioning earlier about abstraction and reasoning in a very different way and very efficient communication. Part of the reason we can learn very efficiently is because language lets us do that summarization. I think language is particularly interesting because it gives us one of those multimodal ways of learning. So when we couple language with images and sound, then one of the problems that generative models have themselves is that they cannot learn consistent elements. So there's issues of physical consistency. If I learn a generative model of videos and I ask it to go forward, 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 it doesn't know that this is a solid object, so walls start disappearing, and so you need to learn that. If I take a generative model of a sequential system that goes in a circle, there's this loop closure problem. If I go in the circle, I should eventually see the same thing I started with, but there's no temporal consistency in this case, so then these models start imagining all sorts of things. So language is one way of really grounding these kind of simulators and simulations in that kind of physical consistency that we can use to describe the world in abstract. So anyway, I love language. I'm working on some projects in language, so it's fun to work on because they have a very different structure, very high dimensional data, very sparse data, which is very different from images. They are high dimensional, but they are not sparse. And so there's something interesting to do there.
I guess that relates to one of your first slides about the social aspects of intelligence. And if we think that artificial general intelligence is a social intelligence, then it's difficult to think of that without language being part of that.
Yeah, I think language has this very core role as we think about building a human-centered AI, right? Not just an arbitrary AI, one that has those issues of ethics and morality and all these kind of issues. So, yeah.
Thank you, Shakir, for a fantastic talk. Let's thank the speakers again.